1,800 light-years from here, there's a planet orbiting a star nearly identical to our Sun. It takes 385 days to complete one orbit, sits in the habitable zone, and might just be the closest thing to Earth we've ever found. But here's what makes it truly unsettling: it's been sitting in that perfect spot for 6 billion years. That's Earth 2.0, or as scientists call it, Kepler-452b. And it's not just another distant world in the catalog of exoplanets. It's a mirror that might be showing us our own future. On July 23, 2015, NASA held a press conference that sent ripples through the scientific community. They'd found something extraordinary, not because it was the largest exoplanet ever discovered or the closest or the most bizarre, but because for the first time in history, astronomers had identified a world that checked every single box: Earth-sized, habitable zone, Sun-like star. The discovery came exactly 20 years after the first planet orbiting a Sun-like star was confirmed. 2 decades of searching, thousands of candidates examined, and finally, something that looked genuinely, startlingly familiar. Let's talk about what makes a planet Earth's cousin rather than just another rock in space. First, size matters, but not in the way you'd think. Kepler-452b isn't Earth's twin. It's 60% larger in diameter, placing it firmly in the category scientists call super-Earths. Its radius measures roughly 1.63 times that of our home planet. When you're standing on its surface, assuming you could, you'd notice immediately that something feels different. The gravity. Oh, the gravity. With an estimated mass 5 times greater than Earth's, Kepler-452b pulls with nearly double our planet's gravitational force. Every step would feel like you're carrying another person on your back. Your bones would compress under the strain. Your cardiovascular system would work overtime just to pump blood upward. A simple walk across flat ground would become an exhausting trek. This isn't science fiction speculation. It's basic physics applied to a world we can measure from 1,800 light-years away. But size and gravity are just the beginning. What really matters is where this planet sits in relation to its star. Kepler-452b orbits at a distance of 1.04 astronomical units from its host star. 1 AU is the distance between Earth and the Sun, about 93 million miles. So Kepler-452b sits almost exactly where Earth does, just slightly farther out. Its orbit is circular, not elliptical, which means consistent conditions year-round rather than wild swings between scorching summers and frozen winters. The year there lasts 385 Earth days. 5% longer than ours. Barely noticeable if you were keeping a calendar. Temperature-wise, models suggest an equilibrium temperature of about 265 Kelvin. That's roughly -8 degrees Celsius or 17 degrees Fahrenheit. Sounds cold, right? But that's the equilibrium temperature, the baseline before you factor in atmospheric greenhouse effects, cloud cover, and all the complex climate dynamics that determine what you'd actually experience standing on the surface. Current climate models, when they account for Kepler-452b receiving 10% more energy from its star than Earth receives from the Sun, suggest mean global temperatures around 307 Kelvin. That's about 34 degrees Celsius or 93 degrees Fahrenheit. Warmer than Earth's average of 289 Kelvin, but still well within the range where liquid water could exist. And liquid water is the key to everything we understand about habitability. The star itself deserves attention because this is where things get genuinely eerie. Kepler-452, the host star, isn't just similar to our Sun. It's almost identical. Same spectral type, G2. Same temperature, 5,757 Kelvin compared to the Sun's 5,778 Kelvin. Same mass, give or take 3.7%. If you could somehow stand on Kepler-452b and look up at the sky, you'd see something that looks exactly like our Sun, maybe slightly larger, maybe a touch brighter, but fundamentally the same warm yellow star that's been rising over Earth for billions of years. This similarity isn't just cosmetically interesting. It's profoundly important for understanding habitability. Red dwarf stars, which make up about 70% of all stars in our galaxy, present serious problems for life. They're prone to violent flares that strip away planetary atmospheres. Planets around them need to orbit so close to stay warm that they become tidally locked, one side eternally facing the star, the other locked in permanent darkness. The radiation environment is harsh, dominated by X-rays and ultraviolet light. Kepler-452 doesn't have these problems. It's a stable, well-behaved middle-aged star that's been burning steadily for 6 billion years. And that brings us to perhaps the most staggering fact about this system. Kepler-452b has been sitting in the habitable zone of its star for over 6 billion years. Think about what that means. Life on Earth emerged roughly 3.8 billion years ago. It took another 3 billion years for complex multicellular organisms to appear. Humans showed up in the last few 100,000 years, a blink of an eye in geological time. If life arose on Kepler-452b, it's had 1.5 billion years more than Earth to evolve. An entire geological era's worth of additional time for chemistry to become biology, for simple cells to become complex organisms, for intelligence to potentially emerge. This doesn't mean life exists there. But if it does, and if it followed a trajectory even remotely similar to Earth's, we might be looking at a civilization that was building its first cities when Earth was still covered in nothing but microbial mats. The discovery process itself reveals just how far our technology has come in detecting distant worlds. In 2009, NASA launched the Kepler Space Telescope with a single, focused mission: stare at one patch of sky and watch for the tiny, telltale dimming that occurs when a planet crosses in front of its star. This transit method is deceptively simple in concept but extraordinarily difficult in execution. Imagine trying to detect a flea crossing in front of a car headlight from several miles away. That's roughly the scale of the challenge. Kepler monitored about 150,000 stars continuously, measuring their brightness with extraordinary precision. When Kepler-452b passed between its star and Earth, it blocked a minuscule fraction of the star's light. We're talking about a dimming of less than 1%, lasting just a few hours, occurring once every 385 days. The first transit was detected. Then another, 385 days later. Then another. The pattern was consistent, the timing precise. This wasn't instrumental noise or stellar activity. Something was orbiting Kepler-452, and its size and orbital period could be calculated from the depth and duration of those dips in starlight. But Kepler's data alone wasn't enough for confirmation. Ground-based telescopes at McDonald Observatory in Texas, the Fred Lawrence Whipple Observatory in Arizona, and the W.M. Keck Observatory in Hawaii all turned their instruments toward Kepler-452. They needed to rule out false positives, binary star systems that could mimic planetary transits, background eclipsing binaries, or other astronomical phenomena that might fool even sophisticated detection algorithms. The observations confirmed it. Kepler-452b was real. Or was it? In 2018, a study by Mullally and colleagues threw statistical cold water on the discovery. They argued that based on the available data, Kepler-452b had not been definitively proven to exist. It remained, in their assessment, a candidate rather than a confirmed planet. This kind of scientific debate is healthy, even necessary. Extraordinary claims require extraordinary evidence, and a planet that's been called Earth 2.0 demands rigorous scrutiny. But by 2025, further analysis had pushed the false positive probability below 1%. The planet almost certainly exists. The debate highlights an important truth about exoplanet science. We're working at the absolute edge of our observational capabilities, detecting worlds so distant and dim that confirming their existence requires multiple independent lines of evidence and years of careful analysis. 1,800 light-years. That distance creates a fundamental barrier to understanding Kepler-452b in detail. Even traveling at the speed of light, which nothing with mass can do, it would take 1,800 years to reach this planet. The New Horizons probe, one of the fastest objects humans have ever built, travels at about 59,000 kilometers per hour. At that speed, the journey would take 30 million years. Current telescopes, even next-generation instruments like the James Webb Space Telescope, can't resolve Kepler-452b's atmosphere or determine its precise mass. It's too far away, its light too faint, its signal too mixed with the overwhelming glare of its parent star. We can measure its size from transit depth. We can calculate its orbital period from transit timing. We can estimate its temperature based on stellar luminosity and orbital distance. But we can't see its surface. We can't analyze its air. We can't definitively say whether it's a rocky world with oceans and continents or a water world with no land at all. Everything we know about Kepler-452b comes from inference, modeling, and comparison with planets we understand better. It's detective work conducted across an almost incomprehensible gulf of space. Yet despite these limitations, or perhaps because of them, Kepler-452b occupies a special place in our search for other worlds. It represents a milestone, a proof of concept that planets like Earth orbiting stars like the Sun actually exist out there in the galaxy. And if one exists, there are likely millions more. The question isn't whether Earth-like planets exist. Kepler answered that. The question is what these worlds are actually like, whether they harbor life, and what that life might have become over billions of years of evolution under alien suns. To understand those possibilities, we need to look deeper into what makes Kepler-452b potentially habitable, and what might make it hostile. The habitable zone. Scientists call it the Goldilocks zone, that narrow band around a star where temperatures allow liquid water to exist on a planet's surface. Not too hot, not too cold. Just right. But that's a dangerously simple way to think about habitability. Kepler-452b sits right at the inner edge of its star's habitable zone, receiving 10% more energy than Earth gets from the Sun. 10% doesn't sound like much. It's the difference between a comfortable room and one that's slightly warm. But on a planetary scale, that extra energy changes everything. Earth plants would photosynthesize just fine under Kepler-452's light. The star's spectrum is nearly identical to our Sun's, so chlorophyll would work exactly as it does here. Stand on Kepler-452b's surface and look up, assuming you could survive the double gravity and whatever else awaits there, and you'd see a star that looks almost exactly like home. Maybe slightly larger, noticeably brighter, but unmistakably sun-like. The daylight would feel familiar. Shadows would fall at familiar angles. The color temperature of the light hitting your hypothetical spacesuit would be nearly indistinguishable from Earth's. But that extra 10% of stellar flux is a warning sign written in physics. Climate models suggest Kepler-452b's mean global temperature might reach 34 degrees Celsius. That's 93 Fahrenheit. Earth's average is about 15 Celsius, 59 Fahrenheit. The difference pushes Kepler-452b into a thermal regime we'd recognize as perpetually tropical, with no polar ice caps and significantly more water vapor in the atmosphere. Water vapor is a greenhouse gas. More heat means more evaporation. More evaporation means more water vapor. More water vapor traps more heat. The feedback loop is self-reinforcing, and it's the same process that turned Venus into hell. Scientists call it the runaway greenhouse effect, and Kepler-452b is walking a knife's edge. Here's where things get interesting. Kepler-452 is 6 billion years old, 1.5 billion years older than our Sun. Stars brighten as they age. It's a consequence of how fusion works in their cores. Over billions of years, helium ash builds up, the core contracts slightly, temperatures rise, and fusion rates increase. The star gets hotter, more luminous, and the habitable zone moves outward like a slow tide. Kepler-452 is entering the phase of its life where this brightening accelerates. Within the next 500 million years, maybe less, the star's increasing luminosity will push so much energy onto Kepler-452b that any oceans will begin to boil. Water vapor will flood the atmosphere. The greenhouse effect will spiral out of control. The planet will transition from potentially habitable to definitively dead, transformed into a steam-shrouded furnace where surface temperatures climb into the hundreds of degrees. Unless it already happened. We don't know if Kepler-452b has oceans right now. We don't know if it ever did. The planet might already be in the early stages of runaway greenhouse warming, its surface hidden beneath impenetrable cloud decks of water vapor and sulfuric compounds, its fate sealed by the inexorable physics of stellar evolution. But there's a counter-argument. Kepler-452b's larger mass, roughly 5 times Earth's, gives it stronger gravity. Stronger gravity holds onto atmospheres more tightly. On a smaller world like Earth, water molecules in the upper atmosphere can be broken apart by ultraviolet radiation, with hydrogen escaping to space while oxygen oxidizes surface rocks. It's a slow leak that eventually dries out a planet. Mars lost most of its water this way. Venus probably did too, after its oceans boiled. Kepler-452b's gravity might prevent this. The planet could hold on to its water for an additional 500 to 900 million years, even as its star brightens. That's not salvation, just a stay of execution. Eventually, the star wins. But those extra hundreds of millions of years could be the difference between a dead world and one where life still clings to existence, adapted to increasingly hostile conditions. Assuming, of course, that Kepler-452b is rocky. That's still not certain. Planets between 1.5 and 2 times Earth's radius occupy an ambiguous category. Some are rocky super-Earths with thick atmospheres. Others are mini-Neptunes, worlds with small rocky cores surrounded by massive hydrogen and helium envelopes. Kepler-452b sits right at the boundary, 60% larger than Earth, with a composition probability between 49 and 62% for a rocky surface. If it's a mini-Neptune, the discussion of surface habitability becomes meaningless. There is no surface, just increasing pressure and temperature as you descend through layers of gas until you reach a core that might be liquid or solid but is definitely inhospitable. The planet would still technically orbit in the habitable zone, but it wouldn't be habitable in any sense we'd recognize. If it is rocky, the higher mass creates consequences beyond just stronger gravity. More mass means more internal heat. Earth's interior is kept molten by radioactive decay of elements like uranium and thorium, plus leftover heat from the planet's formation. A planet 5 times more massive would have proportionally more radioactive material and would have started with more primordial heat. That means more volcanic activity, possibly much more. volcanic activity isn't necessarily bad for habitability. On Earth, volcanoes are part of the carbonate-silicate cycle, a planetary thermostat that regulates atmospheric carbon dioxide over geological timescales. When the planet gets too warm, increased rainfall and weathering pull CO2 from the air and lock it into rocks. When the planet gets too cold, reduced weathering allows volcanic outgassing to build up CO2 and warm things back up. It's a negative feedback loop that's kept Earth habitable for billions of years. A more volcanically active Kepler-452b might have a more robust version of this cycle, actively buffering against the increasing stellar luminosity. The planet could regulate its temperature more effectively than Earth does, potentially extending its habitable lifetime by hundreds of millions of years. But there's a limit. Eventually, no amount of geological regulation can overcome a star that's pumping too much energy onto the surface. The thick atmosphere that models predict for Kepler-452b would create perpetual cloud cover. If you could somehow stand on the surface and look up, you might never see the stars. The sky would be a uniform white or gray, with the sun a diffuse glow rather than a distinct disk. Weather would be extreme. More atmospheric mass means more energy available for storms. Hurricanes on Kepler-452b could make Earth's worst tropical cyclones look gentle. Doubled gravity affects everything. Rain falls faster. Winds blow differently. The atmosphere is compressed into a narrower layer, making the surface pressure higher than Earth's even if the total atmospheric mass were the same. But it probably isn't the same. A planet with stronger gravity can hold on to lighter gases more easily, potentially retaining a thicker atmosphere over billions of years. That doubled gravity would reshape any life that evolved there. Nothing could be tall and spindly. Everything would be built low to the ground, compressed, sturdy. Trees, if they existed, would be wider than they are tall, with massive trunks to support their weight. Animals would have shorter, thicker limbs. Flight would be harder, requiring larger wingspans or more powerful muscles. Everything would be built like it's expecting to be crushed. For humans, the physiological challenges would be severe. Standing up would feel like carrying another person on your back. Walking would be exhausting. Your heart would struggle to pump blood against the increased gravitational load. Your bones would compress. Long-term exposure could lead to orthopedic problems, cardiovascular stress, and chronic fatigue. We're built for Earth's gravity. Kepler-452b would break us. But we're getting ahead of ourselves. We don't know if there's even a solid surface to stand on. We don't know the atmospheric composition. We don't know if there's water. Everything we're discussing is inference built on inference, models stacked on assumptions, educated guesses constrained by physics but not confirmed by observation. What we do know is this. Kepler-452b has orbited in the habitable zone of a sun-like star for over 6 billion years. Earth has been in our habitable zone for about 4.6 billion years. Life on Earth appeared relatively quickly, within a few hundred million years of the planet becoming habitable. If the same timeline applied to Kepler-452b, life there could have had an extra 1.5 billion years to evolve, adapt, and diversify. That's enough time for everything to be different. Life on Earth took 3 billion years to move from single cells to complex multicellular organisms. Another 1 billion to develop animals. Another few hundred million to crawl onto land. If Kepler-452b followed a similar trajectory but started earlier, its biosphere could be unrecognizably advanced compared to ours. Or it could have hit dead ends we haven't encountered. Or it might never have started at all. The planet's age cuts both ways. More time for life to develop also means more time for catastrophes to occur. Asteroid impacts, nearby supernovae, gamma-ray bursts, massive volcanic events, any of these could have sterilized the planet multiple times over. Earth has had several mass extinctions. Kepler-452b has had billions of years to accumulate its own collection of disasters. And now, as its star enters the final stages of main sequence evolution, Kepler-452b faces its ultimate test. The star Kepler-452 is 6 billion years old. Our Sun is 4.6 billion. That 1.5 billion-year difference matters more than you might think. Stars don't shine at constant brightness throughout their lives. They evolve. They change. And right now, Kepler-452 is entering a phase our Sun won't reach for another 1 billion years. As stars age, they grow brighter. It's counterintuitive. You'd think they'd dim as they burn through their fuel. But the opposite happens. Helium builds up in the core from hydrogen fusion. That helium-rich core contracts under its own gravity, getting denser and hotter. The increased temperature accelerates fusion in the surrounding hydrogen shell. More fusion means more energy output. The star brightens. For Kepler-452, this process has been underway for 6 billion years. It's already about 20% more luminous than our Sun. That extra light translates directly into extra heat for any planets in orbit. Kepler-452b is receiving 10% more energy than Earth gets from the Sun. Not because it's closer to its star, but because its star is intrinsically brighter. 10% doesn't sound catastrophic. But climate systems are sensitive. Small changes in energy input can trigger massive shifts in planetary conditions. On Earth, ice ages and warm periods have been driven by variations in solar energy of just a few percent, changes caused by orbital wobbles and axial tilt shifts. Kepler-452b is dealing with a permanent 10% increase that will only get worse as its star continues to age. This brings us to the runaway greenhouse effect. It's what killed Venus. Once a planet that might have had oceans. Now a hellscape with surface temperatures hot enough to melt lead, crushing atmospheric pressure, and clouds of sulfuric acid. Venus wasn't always like this. Early in the solar system's history, Venus might have been habitable. Then the Sun's increasing luminosity pushed it over the edge. Here's how it works. As a star brightens, the planet receives more energy. Surface temperatures rise. Warmer temperatures increase evaporation. More water vapor enters the atmosphere. Water vapor is a greenhouse gas, far more effective at trapping heat than carbon dioxide. The increased water vapor traps more heat, which raises temperatures further, which evaporates more water, which traps more heat. It's a feedback loop with no natural break. Eventually, temperatures climb so high that all surface water evaporates. The atmosphere becomes saturated with water vapor. Ultraviolet radiation from the star breaks apart water molecules in the upper atmosphere, splitting them into hydrogen and oxygen. Hydrogen, being light, escapes to space. The planet loses its water permanently. What's left is a thick atmosphere of carbon dioxide and other gases, creating extreme greenhouse warming with no water to moderate it. Venus went through this. Mars might have too, though its story is complicated by its small size and weak gravity. Kepler-452b is next in line. The question is when. Models suggest Kepler-452b might have another 500 million years before the runaway greenhouse effect becomes inevitable. maybe as much as 900 million years if certain factors work in its favor. But that's assuming the planet has oceans to lose in the first place. If it's already a dry world, the runaway greenhouse scenario is moot. If it never had significant water, there's nothing to evaporate. The planet's size becomes relevant here. Kepler-452b has about 5 times Earth's mass. That means stronger gravity. Stronger gravity holds onto atmospheric gases more effectively. Light gases like hydrogen and helium, which Earth struggles to retain, stick around longer on more massive planets. More importantly, stronger gravity means higher atmospheric pressure at the surface. Higher pressure raises the boiling point of water. On Earth at sea level, water boils at 100 degrees Celsius. On a planet with twice the surface pressure, water wouldn't boil until significantly higher temperatures. This gives Kepler-452b a buffer. Even as temperatures rise, its oceans, if they exist, can remain liquid longer than they would on a less massive planet. This is the planet's advantage in a race against stellar evolution. Its star is getting brighter, pushing it toward a runaway greenhouse. But its mass is buying time, allowing it to hold on to water under conditions that would boil Earth's oceans away. The two forces are in opposition. Which one wins determines the planet's fate. If Kepler-452b has active plate tectonics, that changes everything. Plate tectonics drive the carbonate-silicate cycle, one of Earth's most important climate regulation mechanisms. Here's how it works. Carbon dioxide in the atmosphere dissolves in rainwater, forming weak carbonic acid. This acid weathers rocks, breaking down silicate minerals. The weathering products wash into the ocean, where marine organisms use them to build shells made of calcium carbonate. When these organisms die, their shells sink to the ocean floor, eventually getting subducted into the mantle at tectonic plate boundaries. Deep underground, heat and pressure break down the carbonates, releasing carbon dioxide, which returns to the atmosphere through volcanic eruptions. This cycle acts as a planetary thermostat. If temperatures rise, weathering accelerates. More carbon dioxide gets pulled from the atmosphere and locked into rocks. With less atmospheric carbon dioxide, the greenhouse effect weakens, and temperatures drop. If temperatures fall, weathering slows. Carbon dioxide accumulates in the atmosphere from volcanic outgassing, strengthening the greenhouse effect, and temperatures rise. It's a negative feedback loop that has kept Earth's climate relatively stable for billions of years despite the sun's increasing luminosity. Kepler-452b's larger mass means more internal heat. More heat drives more geological activity. More volcanic eruptions, more tectonic movement, a more vigorous carbonate-silicate cycle. This could extend the planet's habitable window significantly, potentially adding another 500 to 900 million years before the runaway greenhouse becomes unstoppable. But there's a limit. Eventually, the star gets too bright. The feedback mechanisms can't compensate anymore. Temperatures cross a threshold where water vapor dominates the atmosphere and the runaway begins. No amount of geological activity can prevent it once it starts. So where is Kepler-452b in this timeline? We don't know. The planet could be in its prime, with stable oceans and a functioning carbon cycle keeping temperatures in check. It could be on the edge, with rising temperatures beginning to stress its climate systems. Or it could have already crossed the line, its oceans boiling away, its atmosphere thick with steam, its surface transitioning from habitable to hostile. The star's age tells us the clock is ticking. 6 billion years is old for a sun-like star still in the main sequence. Kepler-452 has maybe another billion years, possibly 2, before it exhausts its core hydrogen and begins evolving into a red giant. When that happens, it will swell to enormous size, its outer layers expanding outward. Kepler-452b, currently in the habitable zone, will be engulfed. But long before that, long before the star becomes a red giant, the planet will have lost any habitability it once had. This creates a strange temporal window. If life exists on Kepler-452b, it's living on borrowed time. The planet's star is aging faster than ours. Its habitable period is shorter. Whatever evolutionary processes might be unfolding there are constrained by a deadline Earth hasn't reached yet. Think about what that means. Earth has potentially another billion years before our sun's increasing luminosity makes the planet uninhabitable. Maybe more if our carbonate silicate cycle holds up. Kepler-452b might have only 500 million years left. Half as long. If intelligent life evolved there, it faces a hard limit. Leave the planet or die with it. No extensions. No delays. This assumes, of course, that the planet is habitable now. That it has water. That it has the right atmospheric composition. That its geology is active enough to regulate climate but not so active that the surface is uninhabitable. Every one of these is an assumption built on incomplete data. What we can say with confidence is this. Kepler-452b orbits an aging star. That star is getting brighter. The planet is receiving more energy than Earth does. If it has oceans, those oceans are warming. If it has ice caps, they're melting. If it has a climate system, that system is under stress. The physics is clear. The trajectory is set. And the planet's response to these changes will determine whether it remains a living world or becomes another dead rock orbiting a dying star. Which brings us to the real question. What would you actually see if you could somehow stand on Kepler-452b's surface? Start with the sky. Look up. The star would appear almost exactly like our sun. Same color. Same brightness to your eyes. The difference would be subtle. 20% more luminous, yes, but from the ground, standing there, you wouldn't necessarily notice. The light would feel familiar. Warm. Not alien. But that's where familiarity ends. The horizon would curve differently. Not drastically, but enough that if you were paying attention, you'd notice. Kepler-452b is 60% larger in diameter than Earth. Stand at sea level on Earth and the horizon sits about 3 miles away. On Kepler-452b, it would extend further. Maybe 4.5 miles depending on atmospheric conditions. The world would feel bigger because it is bigger. Gravity changes everything else. 60% more radius. 5 times Earth's mass. Surface gravity approximately double what you're used to. Every movement becomes work. Walking feels like hiking uphill. Running? Forget it. Your legs would give out in minutes. Your body, evolved for 1G, suddenly weighs twice what it should. Your skeleton strains under the load. Your heart works overtime pumping blood upward against the pull. Standing upright for extended periods becomes exhausting. This isn't speculation. We know how human physiology responds to increased gravity from centrifuge experiments and studies on hypergravity effects. Muscles fatigue faster. Bones experience greater stress. Cardiovascular systems struggle. Astronauts returning from low-gravity environments face serious adaptation challenges. Now reverse that. Take someone from 1G and drop them into 2G. The adjustment would be brutal. But you wouldn't just feel heavier. Everything would feel heavier. Drop a rock. It falls faster. Throw a ball. It arcs downward quicker than your brain expects because your brain evolved calculating trajectories in Earth gravity. Every physical intuition you have about how objects move would be wrong. You'd need to relearn basic motor skills. Water would behave differently too. Rain would fall harder. Each droplet carrying more kinetic energy. A gentle rain on Earth becomes a stinging shower on Kepler-452B. Rivers would cut deeper channels. Erosion would proceed faster. Waterfalls would hit with greater force. The entire hydrological cycle would operate in a higher energy state. Now add the atmosphere. Models suggest Kepler-452b likely has a thick atmosphere. Thicker than Earth's. Why? Larger mass means stronger gravity. Stronger gravity holds onto atmospheric gases more effectively. The planet can maintain a denser envelope of air. This has consequences. Thicker atmosphere means higher surface pressure. Possibly significantly higher. We don't know the exact value, but if the atmosphere is substantially denser than Earth's, you're looking at pressures that would require specialized equipment. Not necessarily diving suit levels, but enough that breathing would feel different. Heavier. Each breath requiring more effort to expand your lungs against both the external pressure and the double gravity pulling down on your chest. The thick atmosphere would scatter light differently. The sky might not be blue. Could be deeper. Could have different color tones depending on atmospheric composition. Sunsets would paint the sky in hues we can't predict without knowing what gases dominate. Earth's blue sky comes from Rayleigh scattering of nitrogen and oxygen molecules. Change the composition, change the color. And those clouds. Thick, misty clouds covering much of the surface according to models. The increased gravity would affect cloud formation. Heavier water vapor molecules pulled downward more strongly. Clouds might sit lower in the atmosphere. Weather systems would develop differently. Storms could be more intense or more frequent because there's more energy in the system. That extra 10% stellar energy has to go somewhere. Much of it drives atmospheric circulation. Temperature. Models estimate a mean global annual temperature around 34 degrees Celsius. That's 93 Fahrenheit. Warm. Significantly warmer than Earth's average of about 15 Celsius. No ice caps in this scenario. Polar regions exist, but they're not frozen. The entire planet operates in a warmer state. This creates a different climate distribution. No Arctic. No Antarctic. Temperature gradients would be less extreme from equator to poles. Weather patterns would reflect that. Different wind systems. Different ocean currents if oceans exist. Speaking of oceans, do they exist? We don't know. The planet's position in the habitable zone suggests liquid water is possible. The temperature estimates suggest it's likely. But we can't confirm it. Kepler-452b is too far away for current or near-future telescopes to detect water signatures. We're working from theoretical models based on the planet's size, mass estimates, and stellar energy input. The models say water is probable. Reality might disagree. If oceans do exist, they'd be warmer than Earth's. Thermal expansion would make sea levels higher relative to the size of ocean basins. Warmer water holds less dissolved oxygen. Marine life, if it exists, would need to adapt to lower oxygen concentrations. Or the planet's biology might work differently. Use different chemistry, different metabolic pathways. We're assuming Earth-like biochemistry because it's all we know, but that's an assumption. The land masses would tell a story too. Higher gravity affects geology. Mountains can't grow as tall. Earth's tallest peaks exist at the limit of what rock strength can support against gravity. Double the gravity, have the maximum mountain height approximately. Kepler-452B might have mountains, but Everest-scale peaks become impossible. The tallest mountains would be shorter, broader, more stable. Volcanic activity would be intense. 5 times Earth's mass means more radioactive elements in the interior. More decay. More heat. The planet's core stays molten longer. Geological activity continues stronger and longer than Earth's. Volcanoes would be common. Active. Lava flows reshaping the surface regularly. Tectonic plates moving, grinding, creating earthquakes more frequently or with greater intensity. The planet's surface would be younger on average. Less time for erosion to wear down features before volcanic activity refreshes them. This creates a dangerous surface. Beautiful perhaps, but hostile. Frequent earthquakes. Active volcanoes. Thicker atmosphere with potentially toxic or irritating gases from volcanic outgassing. Higher surface pressure. Crushing gravity. Intense rainfall. Weather systems more energetic than Earth's. And all of this under a sun that's slowly getting brighter, pushing the planet toward the edge of habitability. But here's what we keep coming back to. None of this is confirmed. Every detail is extrapolation from limited data. We know the planet's size. We know its orbital period. We can estimate mass. Everything else? Educated guessing based on planetary science principles. The atmosphere could be thin. The surface could be dry. The geology could be quiet. We're describing the most probable scenario, not the only scenario. The planet could surprise us completely. It might have characteristics we haven't considered. Unusual magnetic field strength affecting atmospheric retention. Strange axial tilt creating unexpected climate patterns. A large moon stabilizing rotation and creating tides that affect habitability. We don't know about any of these because detecting them from 1800 light-years away with current technology is impossible. What we can say is this. If you somehow stood on Kepler-452b's surface, you would know immediately you weren't on Earth. The gravity alone would tell you. The sky might look familiar, but everything else would remind you this is an alien world. Similar to Earth in some ways. Orbiting a sun-like star at an Earth-like distance. But different in the details that matter for actually living there. And those details matter enormously. Because the question isn't just whether Kepler-452b is habitable in theory. It's whether anything actually lives there. Whether life arose in those warm oceans, if they exist. Whether that life survived 6 billion years of stellar evolution and planetary change. Whether it evolved complexity. Whether it developed intelligence. Whether, right now, something on that distant world is looking up at its sky, wondering if other worlds exist, maybe even detecting a faint star in their sky that happens to be our sun, wondering if anyone is looking back. We've been looking. The SETI Institute started scanning Kepler-452B for radio signals almost immediately after the announcement. The Allen Telescope Array in California, 42 dishes pointed at that distant star system, listening across billions of frequency channels, searching for any hint of artificial transmission, any pattern that couldn't be natural, any sign that someone is broadcasting. So far, silence. Silence doesn't mean absence. Radio signals are just one way to communicate, and maybe not even a particularly good one for advanced civilizations. We broadcast radio for less than a century before shifting to fiber optics, satellite communications, directed transmissions. Our radio footprint is already shrinking. An alien civilization 1,000 years ahead of us might have abandoned radio completely. Or they use it in ways we don't recognize. Frequency hopping spread spectrum. Quantum encrypted channels. Communication methods we haven't imagined yet. Or they're listening, not broadcasting. Waiting to see who else is out there before announcing themselves. Which is arguably the smart play. The silence could also mean timing. Space is vast, but time is vaster. A civilization might have risen and fallen on Kepler-452B a billion years ago. Or it might arise a billion years from now. The window where two civilizations exist simultaneously and can communicate. Vanishingly small across cosmic timescales. We might be shouting into an empty room, or at people who won't exist for eons, or at ruins that remember nothing. But let's assume the optimistic scenario. Life exists on Kepler-452b right now. What would it look like? Start with the basics. Higher gravity means everything that evolved there would be built differently. Stronger bones. Denser muscle. Lower center of mass for stability. Imagine terrestrial animals built like bulldogs, not greyhounds. Thick, powerful, close to the ground. Flying creatures would need enormous wingspans relative to body size, or extremely powerful flight muscles, or both. The energy cost of flight in twice Earth's gravity is prohibitive. Birds on Kepler-452b, if they exist, might be rare, specialized, nothing like the casual flight we see on Earth. Plants would face similar constraints. Tall trees become engineering problems. The taller a structure, the more mass, the more gravity pulls. Redwoods work on Earth. On Kepler-452b, doubtful. Forests there might be low, dense, sprawling rather than reaching upward. Vegetation built horizontally instead of vertically, which affects everything else. No tall canopy means different light distribution. Different ecological niches. Different evolutionary pressures. Water would behave differently too. Rivers would flow faster, erode more aggressively. Rain would fall harder. Each droplet carrying more kinetic energy. Storms would be more violent. Ocean waves would crash with greater force. Coastal erosion would reshape shorelines faster. The geology itself would reflect this. Mountains erode quicker. Valleys deepen faster. the landscape constantly reshaped by water moving under higher gravity. Then there's the heat. 10% more stellar energy doesn't sound like much until you run the numbers. Earth's average temperature is about 15 degrees Celsius. Kepler-452B's models suggest around 34 degrees. That's approaching the upper limit for complex life as we know it. Tropical everywhere. Poles still warmer than most of Earth's temperate zones. This creates a different climate engine entirely. More evaporation. More rainfall. More energetic weather systems. Hurricanes that make ours look tame. Atmospheric circulation patterns completely unlike Earth's. Life adapted to those conditions would be fundamentally different. Heat tolerance would be baseline. Cooling mechanisms would be crucial. On Earth, animals in hot climates developed various strategies. Large ears to radiate heat. Sparse fur. Behavioral adaptations like nocturnal activity. On Kepler-452b, those strategies would be universal. Everything needs a way to dump excess heat. Maybe larger surface area to volume ratios. Maybe biological cooling systems we haven't seen. Maybe something else entirely. The oceans would be warm. Warm water holds less dissolved oxygen. Marine life would need to be efficient at extracting what little oxygen is available, or live in shallower waters where photosynthesis keeps oxygen levels higher. Deep ocean life might be sparse. Most biological activity concentrated near the surface. Coral reefs, if they exist, would dominate. Massive structures built over millions of years, thriving in warm, oxygen-poor waters because coral is already adapted to those conditions on Earth. Scale that up. Imagine reef systems covering entire continental shelves. Now add 6 billion years of evolution. Earth's complex life took about 600 million years to go from simple multicellular organisms to humans. Kepler-452b had 10 times that duration in the habitable zone. What could evolve in 6 billion years? We can't really imagine. Evolution doesn't follow a preset path. It responds to environmental pressures, random mutations, catastrophic events, ecological opportunities. 6 billion years is enough time for life to emerge, go extinct, emerge again, diversify, collapse, rebuild, over and over. Multiple mass extinctions. Multiple evolutionary radiations. Complexity building on complexity. Intelligence might have emerged. Might have emerged multiple times. Might have destroyed itself and been replaced. Or it might never have emerged at all. Intelligence isn't inevitable. It's one possible evolutionary strategy among many. On Earth, it only appeared once in all the billions of species that ever lived. Maybe intelligence is rare. Maybe it requires specific conditions we don't understand yet. Maybe Kepler-452b is covered in complex ecosystems, rich biodiversity, sophisticated predator-prey relationships, but nothing that thinks about the stars. Or maybe something there surpassed us long ago. 6 billion years in the habitable zone. If life arose early and followed anything like Earth's timeline, intelligent civilization could have emerged billions of years before humans. What could a civilization do with a billion-year head start? We've had technology for maybe 10,000 years. Industrial technology for 250 years. Space technology for 70 years. A civilization a million years ahead would be incomprehensible to us. A billion years? We lack the conceptual framework to even speculate meaningfully. They might have moved beyond biology entirely. Uploaded consciousness into substrates that don't require planetary surfaces. Left the planet for megastructures in space. Spread across their solar system, then nearby stars. Or stayed home and built a civilization so efficient, so sustainable, so integrated with their environment that they're invisible to our detection methods. A truly advanced civilization might not broadcast at all. They might communicate through means we haven't discovered. They might have solved the energy crisis so completely they produce no waste heat we could detect. They might live in such harmony with their planet that their presence leaves no signature visible across 1,800 light-years. Or they might be gone. Civilizations are fragile. Climate change. Resource depletion. War. Pandemic. Asteroid impact. Gamma-ray burst. 1,000 ways for technological civilization to end. Maybe they reached our level, then collapsed. Maybe they reached far beyond our level, then collapsed anyway. Maybe ruins cover Kepler-452B right now. Cities overgrown by vegetation adapted to high gravity and heat. Technology degraded to unrecognizable fragments. Stories forgotten. Just another planet with interesting geology and no memory of what once was. This uncertainty is maddening. We have one data point for life. Earth. One data point for intelligence. Humans. One data point for technological civilization. Us. From a single example, you can't extrapolate universal rules. We don't know if Earth is typical or a bizarre outlier. We don't know if life is inevitable given the right conditions or cosmically rare. We don't know if intelligence emerges readily or almost never. We don't know if technological civilizations usually survive long-term or always destroy themselves. Kepler-452b could answer some of these questions. Not all of them. Even if we detected life there, we'd only have 2 data points. But 2 is infinitely better than 1. 2 lets you start forming hypotheses. 2 suggests patterns. If life arose independently on both Earth and Kepler-452b, that's evidence life is common. If both planets developed complex ecosystems, that's evidence complexity is a natural outcome given enough time. If both developed intelligence, that's evidence intelligence emerges predictably. But we can't get those answers. Not yet. Maybe not ever. 1,800 light-years is too far. Our telescopes can barely detect the planet's existence. Characterizing its atmosphere. Impossible with current technology. Detecting biosignatures. Not happening. Even with next-generation telescopes launching in the coming decades, Kepler-452b will remain too distant, too faint. Those telescopes will target closer exoplanets. Dozens of potentially habitable worlds within 100 light-years. Planets we can actually study. Planets where atmospheric analysis is feasible. Kepler-452b will remain a mystery. A tantalizing possibility. Earth's older cousin, orbiting a sun-like star at an Earth-like distance, potentially harboring life that's had billions of years to evolve. But too far away to confirm. We'll wonder about it. We'll refine our models. We'll make educated guesses. But we won't know. Not in our lifetimes. Probably not in our civilization's lifetime unless we develop faster-than-light travel, which physics currently says is impossible. So what's the point of studying it? Why care about a planet we'll never visit, might never confirm has life, can barely observe? Because it changes how we see ourselves. Before Kepler-452b, before the Kepler mission, we didn't know Earth-like planets around Sun-like stars were common. We suspected, hoped, but didn't know. Now we know. Thousands of exoplanets discovered. Dozens in habitable zones. Several around Sun-like stars. Kepler-452b specifically showed us that Earth isn't unique. Similar planets exist. Statistical analysis suggests billions of them across the galaxy. That realization reframes everything. We're not special. Our planet isn't rare. Our circumstances aren't unique. We're one example of a common phenomenon. Which means life elsewhere isn't just possible. It's probable. Maybe even inevitable. The universe is old. The galaxy is vast. Billions of stars. Billions of planets. Billions of years for chemistry to become biology. For biology to become complexity. For complexity to become intelligence. Human response: I need you to generate part 5 with exactly 1666 words. Please count your words carefully and let me know the exact count. If we're not alone, if intelligent civilizations are common, the Fermi paradox becomes overwhelming. Where is everybody? With billions of potentially habitable planets and billions of years for civilizations to develop, the galaxy should be teeming with evidence. Radio signals. Megastructures. Probes. Something. The silence is deafening. Maybe we're early. Maybe we're among the first technological civilizations to emerge. The universe is only 13.8 billion years old. First-generation stars had no heavy elements. No planets. Second-generation stars started forming planets, but conditions might not have been right for life. Maybe Earth-like planets around Sun-like stars only became common in the last few billion years. Maybe we're pioneers. Or maybe intelligence is rarer than we think. Maybe the jump from simple life to complex life is extraordinarily difficult. Earth had single-celled organisms for over 2 billion years before multicellular life emerged. Maybe that transition is a bottleneck. Maybe most planets with life never get past bacteria. Or maybe complex life is common, but intelligence isn't. Dinosaurs dominated Earth for 165 million years and never developed technology. Intelligence might not be an inevitable outcome of evolution. It might be a fluke. A cosmic accident that rarely repeats. Or maybe civilizations destroy themselves. Maybe every technological species eventually develops weapons capable of planetary destruction. Maybe they all succumb to climate change, resource depletion, nuclear war. Maybe the galaxy is littered with dead civilizations that never made it past their first few centuries of industrialization. Kepler-452b could be evidence for any of these scenarios. If it's lifeless despite billions of years in the habitable zone, that suggests life is rare. If it has simple life but nothing complex, that suggests the jump to complexity is difficult. If it had intelligent life that's now extinct, that suggests civilizations are fragile. Or maybe it's thriving. Maybe Kepler-452b hosts a civilization billions of years old. A civilization that survived its technological adolescence and matured into something stable. Something sustainable. Maybe they've been broadcasting for millions of years and we just haven't detected it yet because we've only been listening for a few decades. The SETI Institute has been scanning Kepler-452b for radio signals. The Allen Telescope Array in California has monitored billions of frequency bands. Nothing. Complete silence. But absence of evidence isn't evidence of absence. Maybe they're not broadcasting. Maybe they use communication methods we haven't thought of yet. Maybe they're deliberately quiet, avoiding contact with younger civilizations. Or maybe they're watching us. If Kepler-452b has a technological civilization with telescopes comparable to ours, they could detect Earth's atmosphere. They could see oxygen, methane, signs of biological activity. Maybe they've been observing us for centuries, waiting to see if we survive our own technological development before making contact. This is pure speculation. We have zero evidence for any of this. But the mere existence of Kepler-452b forces us to consider these possibilities. It makes the abstract concrete. It gives the question of extraterrestrial intelligence a specific address. Not just out there somewhere, but there. In Cygnus. 1,800 light-years away. The planet's discovery also highlights how little we actually know about habitability. We define the habitable zone as the region where liquid water can exist on a planet's surface. But that's based on Earth. One example. What if life doesn't need liquid water? What if it can thrive in liquid methane like on Titan? Or in subsurface oceans like on Europa? Our definition of habitability might be laughably narrow. Kepler-452b fits our Earth-centric definition perfectly. Sun-like star. Earth-like orbit. Potentially rocky composition. But even if it checks all our boxes, that doesn't guarantee habitability. Atmospheric composition matters. Magnetic field matters. Plate tectonics might matter. We don't know enough to say definitively. Climate models suggest Kepler-452b receives about 10% more energy from its star than Earth receives from the Sun. That doesn't sound like much, but it could be significant. Venus receives about twice as much solar energy as Earth and it's a Hell's Cape. Mars receives about half and it's frozen. Planetary climates are sensitive to small changes in stellar input. That extra 10% could push Kepler-452b toward runaway greenhouse conditions. Or maybe not. Maybe its atmosphere compensates. Maybe cloud cover regulates temperature. We can't know without direct observation. The planet's age is both promising and concerning. 6 billion years in the habitable zone is extraordinary. That's 50% longer than Earth has existed. If life arose there, it's had immense time to evolve. But the star is aging. Kepler-452 is about 1.5 billion years older than the Sun and it's entering the phase where it starts to brighten and expand. Eventually, it'll become a red giant and consume the planet entirely. But before that, the habitable zone will shift outward. Kepler-452b will get too hot. Water will evaporate. Greenhouse effects will intensify. Scientists estimate this won't happen for another 500 million years. The planet's stronger gravity might help it retain water longer than Earth could in similar circumstances. 5 times Earth's mass means stronger gravitational pull. harder for atmospheric molecules to escape. That could buy time, but not indefinitely. If Kepler-452b does harbor life, it might be in decline. Maybe it's already experienced runaway greenhouse warming. Maybe its oceans are boiling away right now. Maybe we're looking at a world in its death throes, transitioning from habitable to Venus-like. Or maybe life there has already adapted to warmer conditions. Maybe evolution is keeping pace with the changing climate. Maybe the biosphere is resilient enough to survive the transition. Or maybe intelligent life there saw this coming and left. Maybe they became spacefaring millions of years ago and colonized other worlds. Maybe Kepler-452b is abandoned. A relic. A monument to a civilization that outgrew its birthplace. This is what makes exoplanet science simultaneously thrilling and frustrating. Every discovery raises more questions than it answers. Every new planet is a mystery we can barely investigate. We can detect them. We can measure basic properties. But understanding them, that requires proximity. That requires technology we don't have yet. The James Webb Space Telescope is revolutionizing exoplanet studies. It can analyze atmospheres of nearby planets, detecting chemical signatures that might indicate life. But nearby means within about 100 light years. Kepler-452b is too far. JWST can't help us there. Future telescopes might. Concepts exist for planet imaging telescopes that could directly photograph exoplanets, resolving surface features. But those are decades away. And even then, 1,800 light-years might be too far. So Kepler-452b remains theoretical. A planet we're fairly certain exists, orbiting a star we can barely see, with properties we can only estimate. It's simultaneously the most Earth-like planet we've found and one of the most unknowable. But here's what it definitely does. It proves Earth-like planets around Sun-like stars exist. Before Kepler-452b, we suspected. Now we know. And if one exists at 1,800 light-years, others exist closer. Probably dozens within 100 light-years. Probably hundreds within 1,000. The galaxy is full of them. Planets where water could flow. Where atmospheres could support complex chemistry. Where life might emerge. That changes everything. It means the conditions that led to life on Earth aren't unique. They're replicated throughout the galaxy. Billions of times. The universe isn't hostile to life. It's full of opportunities for it. Whether those opportunities result in actual life is still unknown. Whether any of that life becomes intelligent is still unknown. Whether any of those intelligences survive long enough to become detectable is still unknown. But the opportunities exist. That's confirmed now. Kepler-452b is a mirror. An older, larger version of Earth. A glimpse of what our planet might become billions of years from now when the sun brightens and the habitable zone shifts outward. It's a reminder that habitability isn't permanent. Stars evolve. Planets change. Nothing lasts forever. Earth has perhaps another billion years before the sun's increasing luminosity makes the planet uninhabitable. If humanity survives that long, we'll need to leave. We'll need to become an interstellar species. We'll need to find new homes around younger stars. Stars like Kepler-452 was 6 billion years ago. The cycle continues. Life adapts. Life migrates. Life persists. That's the ultimate lesson from Kepler-452b. Not that we found Earth's twin, but that Earth itself is just one instance of a common pattern. Habitable planets exist. They form around ordinary stars. They persist for billions of years. And if we want to ensure our descendants inherit a future, we need to recognize Earth isn't forever. It's a temporary home. A beautiful, precious, temporary home. Kepler-452b won't answer all our questions. It might not answer any of them definitively. But it's changed how we think about our place in the universe. We're not alone in having the right conditions for life. We're part of a vast cosmic experiment playing out on billions of worlds. Some of those worlds might have succeeded where Earth is still working. Some might have failed. Some might be just beginning. And somewhere out there, 1,800 light-years away, a planet orbits a sun-like star. Maybe it's covered in oceans. Maybe it's teeming with life. Maybe someone there is looking back at us, wondering the same things we're wondering about them. We'll probably never know for certain. But that's not really the point. The point is that we can ask the question now, and it's not absurd. The universe is vast enough, old enough, and full enough of Earth-like worlds that life elsewhere isn't just possible. It's expected. Kepler-452b taught us that. And that knowledge, more than any single planet, transforms how we see ourselves in the cosmos. We don't know what's happening on Kepler-452b right now. That's the frustrating truth. The light we see from that system left 1,800 years ago. When photons from Kepler-452 hit our telescopes today, they're showing us a snapshot from the year 225 CE. The Roman Empire was still standing. The Han dynasty was collapsing. Christianity was spreading through the Mediterranean. Whatever is happening on Kepler-452b today won't be visible to us until the year 3825. This time delay creates a strange disconnect. If an advanced civilization exists there and they're looking back at us, they're seeing Earth as it was 1,800 years ago. No cities. No industrial revolution. No radio signals. Just a blue planet with primitive agriculture and isolated human settlements. They have no idea we've developed technology. No idea we're searching for them. The light carrying evidence of our modern civilization won't reach them for another 1,800 years. We're ships passing in the night across an ocean of time. But maybe that's exactly how it has to work. Maybe the universe's sheer size, combined with the speed of light limit, is a protective mechanism. Maybe young civilizations need isolation. Time to mature. Time to solve their own problems before encountering others. If we could communicate with Kepler-452b in real time, what would we even say? What could they tell us that wouldn't fundamentally alter our development trajectory? The 1,800-year light speed delay isn't a bug. It might be a feature. Think about what Kepler-452b represents beyond just scientific data. It's proof that the conditions for life aren't special. They're common, replicated throughout the galaxy on timescales that dwarf human civilization. 6 billion years that planet has orbited in the habitable zone. 6 billion years of opportunity for chemistry to become biology. For biology to become complexity. For complexity to become whatever comes next. Earth has existed for 4.6 billion years. Life emerged relatively quickly, within a few 100 million years. Intelligence took much longer. Humans are recent arrivals. If Kepler-452b followed a similar timeline but started earlier, life there could be unimaginably advanced. Or it could have hit the same dead ends, the same bottlenecks, the same catastrophes that nearly sterilized Earth multiple times. We're looking at a planet that's had more time than Earth to figure things out. That should terrify and inspire us in equal measure. What if they solved the problems we're struggling with? Climate change, energy, sustainability. What if they built a civilization that lasted millions of years instead of thousands? What if they're still there, having learned lessons we haven't even encountered yet? Or what if they failed? What if Kepler-452b is a warning instead of a promise? A dead world that once thrived but couldn't survive its own success. The silence from our SETI observations doesn't answer these questions. Billions of frequency bands scanned. Nothing detected. But that's expected. Radio is primitive. We've only been broadcasting for a century and we're already moving past it. An advanced civilization wouldn't waste energy on omnidirectional radio broadcasts. They'd use directed beams, quantum communication, methods we haven't imagined yet. Or they'd stay quiet deliberately. The galaxy might be full of civilizations maintaining radio silence, watching, waiting, wondering if anyone else will break first. Smart money says stay quiet. Don't advertise your location until you know who's listening. Kepler-452b forces us to confront uncomfortable possibilities about our own future. The planet is approaching the end of its habitable period. In 500 million years, maybe less, its star's increasing luminosity will boil away any oceans. The runaway greenhouse effect will transform it into another Venus. Dead. Sterile. Uninhabitable. If life exists there now, it's living on a planet with an expiration date. Earth has the same expiration date, just pushed further into the future. Our sun is brightening too. Slowly. Inexorably. In a billion years, Earth will face the same crisis Kepler-452b faces now. The oceans will warm. Water vapor will flood the atmosphere. Greenhouse effects will spiral out of control. Earth's biosphere will collapse. Everything that lives here will die unless it leaves. That's not speculation. That's physics. Stars age. Habitable zones shift. Planets that once supported life become uninhabitable. It's happened before. It'll happen again. Kepler-452b might be showing us our own future. Which means if intelligent life exists there and wants to survive, they have to leave. They have to become an interstellar species. They have to find younger stars with stable habitable zones and start over. That's the ultimate test for any civilization. Can you outgrow your birthplace before your birthplace kills you? Humanity hasn't faced that test yet. We have time. About 1 billion years. But that time will pass. The question is whether we'll be ready. Whether we'll have solved faster-than-light travel, or generation ships, or whatever it takes to move billions of people across light years. Whether we'll have identified target stars and launched missions. Whether we'll have become the kind of species that survives planetary timescales. Kepler-452b suggests this challenge is universal. Every civilization on every planet orbiting every star will eventually face it. The star brightens. The planet dies. Leave or perish. That's the rule. No exceptions. Maybe that's why we don't see evidence of galaxy-spanning civilizations. Maybe most species don't make it. Maybe the jump from planetary to interstellar is too difficult. Maybe civilizations consistently destroy themselves before reaching that point. Or maybe they succeed, but quietly, leaving minimal traces. Maybe the galaxy is full of post-planetary civilizations living in artificial habitats around optimal stars, and we just don't recognize the signatures. We're making assumptions based on one example. Us. One planet. One civilization. One brief moment in cosmic history. Kepler-452b doubles our sample size from 1 to 2, but only if we can confirm what's actually there. And we can't. Not yet. Possibly not ever. The planet will remain a question mark. An intriguing possibility. A reminder that Earth-like worlds exist but remain tantalizingly out of reach. We can detect them. We can measure basic properties. But understanding them, that requires proximity we don't have and technology we haven't built. Future generations might develop telescopes powerful enough to directly image Kepler-452b's surface, to analyze its atmosphere in detail, to detect biosignatures if they exist. But those instruments are decades away at minimum. More likely centuries. By the time we can study Kepler-452b properly, the light we're seeing will be from the year 3000 or beyond. Whatever is happening there now will remain unknown to us until our distant descendants finally have the tools to look. That's assuming our descendants exist. Assuming we survive our own challenges. Climate change. Nuclear weapons. Pandemics. Artificial intelligence. The same threats that might have killed civilizations on Kepler-452b if they ever existed. The same tests every technological species faces. Maybe that's the real value of discovering planets like Kepler-452b. Not the specific data about that particular world, but the realization that we're not unique. The conditions that created us are common. The challenges we face are probably common too. And the outcome, whatever it is, will add one more data point to the galaxy's long experiment with intelligent life. Are we alone? Probably not. The universe is too vast, too old, too full of Earth-like planets for us to be the only ones asking that question. But are we connected? Can we ever communicate with our cosmic neighbors? That's different. Distance and time might ensure permanent isolation. Each civilization developing independently, facing similar challenges, reaching similar conclusions, but never able to share notes. Kepler-452b is out there, orbiting its sun-like star, possibly harboring life, possibly harboring intelligence, possibly harboring nothing but rock and water and chemistry. We'll wonder about it for generations. We'll refine our models, improve our estimates, and maybe, eventually, build telescopes that can actually see it clearly. But until then, it remains what it's always been since we discovered it. A mirror held up to Earth, showing us what we are, what we might become, and what we might have been if circumstances were slightly different. 1800 light-years away, a planet continues its ancient orbit, indifferent to our questions, unknowable in its details, but undeniable in its existence. And that existence, more than any answer it might provide, changes everything.